in flicker, unified it with Einstein. And so here is a falling digits which show something mysterious, all forming a question mark. That's what we are going to discuss today, right now. And of course, this is another image which is dear to my heart. It's something related to inflationary cosmology. And just a quick reminder that if you have something which is called scale field, and if it's initially very large, then the universe enters this stage of exponential expansion, which solves many, many cosmological problems. But the question which I will discuss, I promised you, so this is a moment of scare. Now, but the good thing about it, those who knows what I'm talking about, they will use it like, well, some interesting information, hopefully. For those who don't, they consider looking at it like a piece of art, which you have seen before. So this is Einstein Lagrangian, and that's Lagrangian for the scalar field. So there is nothing terrible. Now this is metric. Okay, this is a metric of expanding universe, and I should, well, I am introducing it to make some things in the future more clear, or at least when we are talking about things where very, very educated people are fighting with each other and thinking badly about each other. Okay, so we will need to have a proper introduction to the subject. So what is so confusing about it? So this is the scale factor of the universe, and this is a three-dimensional part of metric of space-time. That's just normal time, and here is this symbol n in front of it, which tells you that you can measure time differently. You can use bad clock, good clock, or measure time in a distance between galaxies or the scale of the universe. Physics should not depend on it. So that is an interesting point. I can write this metric describing our universe in a very conventional form, and this term write down in whatever way I want. And there must be some invariance, some symmetry of the theory, which tells you that actually it does not matter what kind of clock I am using, because physics should not depend on it. So interestingly, this fact actually means that the total energy of the universe is equal to zero. Because, well, for example, in quantum mechanics, if something depends on time, Hamiltonian, which is energy of the universe, allows you to shift yourself in time. It takes wave function and shifts it in time. So wave function, its derivative with respect to time is proportional to the energy. If it does not really matter in which units I am measuring time, this means that Hamiltonian really does not matter. And that's formal words. I can simplify them many different ways. I can have it, well, a very interesting kiddie discussion for what does it mean, which is not exactly kiddie, which means what is the total energy of the universe. Let's consider a closed universe, for example. Okay, so you have an idea that the total mass creates Newtonian flux of gravitational fields in all directions. That's the same like total charge creates electric field in all directions. And you know that if you surround the charge by a sphere, you will have flux of the electric field equal to the charge inside. That's the Gauss law. For gravitational field, the Gauss law means the total energy inside is equal to the flux of gravitational field through the surface surrounding this source. Okay? This remains true in general theory of relativity, but the total surface of everything doesn't exist. For the closed universe, there is no outer surface which surrounds it, which is a different way of expressing the same thing. The total Hamiltonian of the universe, total energy of the universe is equal to zero, but now this means, from the point of view of quantum mechanics, this means that Schrödinger function, excuse me, this is Schrödinger equation, wave function of the universe over dt is equal to Hamiltonian psi is equal to zero. And this means that the wave function of the universe does not depend on time. Is it lower line visible for people or not? Because it's possible to put something under a projector and then it will become visible. Okay.
No, we can.
What?
We can.
Okay. So because that's so important, the wave function of everything does not depend on time. Let me show you what are implications, like, because this looks paradoxical. It's obviously paradoxical. Because we are talking, I'm talking right now, you're listening, and then I finish, and as if nothing happened, because wave function will not change. Okay, so that's a theorem. That's a correct theorem. So let us show a different paradox of the same nature. What if we use the size of the universe as a measure of time? And some well-educated people, really the best in the business, were trying to do it. It all started from Sakharov in the 60s. Okay, the father of thermonuclear weapon in Soviet Union. Steve Hawking in '85 came to Russia and he told us that actually if the universe, or closed universe, reaches the moment of largest expansion and then start collapsing, then the arrow of time turns. Okay? Why it turns? Well, because in a closed universe, the scale factor reaches the maximum. Scale factor is the only measure of time, because nothing depends on time. Everything depends on scale factor. This wave function, see, this is a scale of the universe. It's okay if the wave function depends on the scale of the universe. It's part of this Wheeler-DeWitt equation, but it should not depend on time. So if it depends only on the scale of the universe, on the size of the universe, if the size of the universe is the only time available, then once the size becomes maximum, then the universe collapses, which means size goes back, then this means that dead will stand up from the grave, because everything will just return to the previous state. And it was obviously silly, and when I tried to argue with Steve about it, well, it was impossible, because equations tell so. So it required Don Page to explain him what happened, and then he considered it the biggest blunder of his life. So every great scientist had a big blunder in his life, and he had this one. But what is the nature of the blunder? In order to understand it, we may go back to '67, because the father of quantum cosmology, Bryce DeWitt, he have written a huge article for Physical Review. The article was so huge that it was lying in Physical Review on review for about a year. Nobody was brave enough to open it because it was terrible, huge, horrible. And eventually the referee said, okay, we will publish it, but only if you divide it into 3 parts. First, well, yeah, right, normal kind of theory, then quantum cosmology, and then applications. Okay, so that is how he missed the priority of finding what was later called Fadeev-Popov ghosts. That's because his paper was too complicated and had too much in it. Okay, so he himself formulated this equation, which was, for whatever reason, called Wheeler-DeWitt equation. He didn't like this equation. He said, no, it is Wheeler equation. Though Wheeler never derived it, but DeWitt didn't like it. So this Wheeler-DeWitt equation, he had seen that wave function of everything doesn't depend on time, so he said, what is the resolution of the paradox? The resolution of paradox is that we are not asking questions why and how the universe depends on time, the whole universe. We're asking why the rest of us, the things that I am observing, depend on my clock, okay, so that my time will be, okay. So then what I'm doing, I'm dividing the universe into 2 parts, into an observer and the rest of the universe.